In relativistic theories, your best friends are going to be quantities which are Lorentz scalars. These are going to be quantities that you can measure, and they do not change when you observe from different viewpoints. We've already learned that time is dilated and lengths are contracted, and all of these things, how you measure them is going to be frame dependent. Lorentz scalars are quantities that are frame independent. That's where we learned that the space-time interval is a Lorentz scalar. That's why we like the space-time interval so much. Another of these is proper time. Proper time is useful because it's going to be a Lorentz scalar, so everyone is always going to agree on proper time. So when I say proper time, a given proper time is going to be associated with a particular world line. So when we want to calculate proper time, the first thing we need to say, well, okay, what world line are we talking about? And then for a given world line, you can calculate this proper time, and everyone is going to agree on that time, regardless of what reference frame they're viewing it from. Okay, so what is it? So proper time along a world line. So when we have a particular proper time we're talking about, it's attached to a particular world line, along a world line. It's going to be the time that's measured by a clock following that world line. So for instance, there is a proper time associated with me, right? As I live my life, I am tracing out some world line in space time. And you could talk about the proper time associated with that world line, the world line of me, of Alex. The amount of time that passes between two events in my life is going to be the time as measured by, for instance, this watch on my wrist, because this watch is going to always be at rest in my world line, assuming it stays on my wrist, right? It's at rest relative to me. And so the time as measured by this watch is my proper time. Now you might be wearing your own wristwatch and you might be moving relative to me and you have your own different proper time. So there are different proper times associated with any frame of reference that you want to think about. And the proper time, though, is going to be measured by a clock at rest in that particular frame of reference that you're focusing on. And the reason this is a Lorentz scalar, so again, if we focus on me and my proper time, everyone, whether you're in my reference frame or not, everyone can look at my watch. I'm holding it up. Everyone can look at it. You're riding past on a train. You can look at it. Anyone can look at my watch. And therefore, we can compare how much time has passed on my watch. And so this gives us sort of a physical way to check that everyone is in agreement, right? Everyone can agree with this. And that's the sense in which it's a Lorentz scalar. No matter what reference frame we are viewing from, the amount of time that passes according to my watch, everyone agrees upon. Right? That is what the principle of relativity teaches us, right? Everyone's going to agree upon that. We haven't broken physics that badly. Okay, so that is the proper time. It's the time is measured by a clock following a world line of the proper time that we're thinking about. And so how can we measure this? So measuring proper time. And I should say I wrote it up above, but I didn't mention it. We often use the Greek letter tau for proper time to differentiate it from, we'll usually use lowercase t to just be some time coordinate in some reference frame. Tau is this special thing, proper time. So how can we measure it? Well, first of all, I might be accelerating. I may or may not be in an inertial reference frame. And you want to still be able to calculate my proper time and talk about it. So the first thing usually we do is we think about taking this world line, my world line in this example, and breaking it up into tiny pieces. where each piece is then going to seem inertial, and we can define some coordinates. And we're going to define the coordinates as t, I'll write them, or tau, excuse me, x sub tau, y sub tau, z sub tau. And these are going to be my instantaneous rest coordinates. And so if we measure a space-time interval, ds squared, which again, we like the space-time interval, it's a Lorentz scalar. With these coordinates, I'm just gonna, I just named these coordinates and I'm going to calculate the space-time interval in these particular coordinates. But remember, because the space-time interval is a Lorentz scalar, I can calculate it using whatever coordinates I like. I just am choosing to use these instantaneous rest coordinates to calculate this particular space-time interval that I'm thinking about. Now, because these are instantaneous rest coordinates, all of these guys, all of these spatial intervals are going to be 0. Again, because these are rest coordinates, where the object that we're focusing on, whether it be me or something else, is at rest. So ds squared, our space-time interval, is equal to simply the infinitesimal proper time squared. So that's sort of helpful, but maybe we want to calculate a finite amount of proper time that has passed. So I'm going to say how much proper time has passed. Well, if we want to consider a finite amount of proper time, we want to add up all of our infinitesimal proper times that have passed, which really at the end of the day means that we want to do some integral, right? Adding up a bunch of tiny elements in the infinitesimal limit is going to really be doing an integral. So we're going to integrate over this. And, oh, I forgot square root, right? Because we don't want delta tau squared. We want delta tau. Now this we just showed can be calculated as the square root of the space-time interval. We just showed that, we can calculate the space-time interval in any reference frame with any set of coordinates that we like. And we just chose these particular ones. And in these particular coordinates, ds squared is equal to d tau squared. So that's all true so far. But we can calculate ds squared in a different reference frame. And so we know this is also equal to integral dt squared minus dx squared minus dy squared minus dz squared, where these t, x, y, z are just some other coordinates. In probably some other reference frame, because we can calculate the space-time interval in whatever reference frame that we like. And now we can do a change of integration variables and write this as 1 minus dx dt squared minus dy dt squared minus dz dt squared. Sorry, that's a little sloppy. It should all be under the square root. And then dt. Now we're integrating over the time coordinate in my other reference frame. Not the proper time one, but the reference frame of the object that we're calculating the proper time of, but potentially some other reference frame, where I'm just using the normal t. And now what you notice is this whole thing is the velocity squared, or minus the velocity squared. So this is the integral of 1 minus v squared dt. So this is the important formula that you need to take away from this video, where again, so what are all of these again? Okay, tau is our proper time. So tau is the proper time of some object. V is the speed of that object in some other frame. So again, maybe I'm the object whose proper time we want to calculate. You're riding past on a train. So you see me as moving. You're always at rest in your own reference frame, right? So you see me as moving with some velocity v as you ride past. So v is that speed that you see me as moving at. And t is your time. So t is the time coordinate in that other frame. All right. So now what we have here is we have this thing called the proper time, which we can measure in any reference frame that we like. Right? So maybe we choose one that's convenient for some reason, and we can measure the proper time in that given reference frame. And this proper time, again, is going to be the time as measured by an observer at rest in the world line that we are in the reference frame of the world line, or whose world line we're considering. Okay, so that's proper time. It's a little bit of an abstract concept, and when students first learn about it, it's a challenging one to wrap your head around. But it's going to be so incredibly useful that it's definitely worth the time, taking that time to try to wrap your head around it. All right, so that's proper time.